let us get started. I will talk about binary symmetric channel, and that binary symmetric channel is described by this picture right here. This diagram. This diagram is the channel. This is for px, where x is equal to 0. I will let the probability be pi and 1 minus pi here, and py is right here. And then we can say that this is probability theta and 1 minus theta. So py is equal to 0 is equal to theta. So that's the channel. That is the input distribution, output distribution. Input distribution is parameterized by a number between 0 and 1. So if we find out what pi has to be in order to achieve the capacity, which is the maximum of mutual information, then we have achieved our goal. Okay, so capacity is maximum over parameter pi of the mutual information. So maximize mutual information by controlling pi, or by finding optimal pi which maximizes mutual information. So we need to find the pi that maximizes the mutual information. So that is the goal, and the problem is set up. So here we want to consider mutual information. In order to do that, basically, we need to consider these two measures, Hy and Hy given x. So entropy of y, entropy of y given x, we have to consider. So let's take a look at this conditional entropy, Hy given x. So Hy given x, so we can decompose this into two, basically H of y given x equal to 0. We can consider this first, and we multiply with the probability that x is equal to 0, and add that with 1 minus pi, where x is equal to 1, and we want to consider entropy of y when x is equal to 1. So if we add the two, that is equal to entropy of y given x. So that's what H of y given x is. All right. Now let's consider one of them. Let's consider this. When x is equal to 0, what is the entropy on y? That depends on P of y given x is equal to 0. That P of y given x is equal to 0, the conditional distribution of y given x is equal to 0 is nothing but 1 minus p and p. So this one, the binary distribution is described by p. right? With the probability 1 minus p, y is equal to 0. With the probability p, y is equal to 1. So this is nothing but entropy on P. Okay, so we have identified this part. Now let's consider this part. Entropy on Y given X is equal to 1. And you realize that P of Y given X is equal to 1 has exactly the same distribution, right? With the probability P, y is equal to 0. With the probability 1 minus P, y is equal to 1. Okay, so the distribution is, again, P and 1 minus P. So entropy is function of distribution only. So this one is H of P again. Okay, so if we add the two, the whole thing becomes H of P. So the mutual information is equal to H of Y minus H of P. That's what we have. And entropy on Y is upper bound, can be upper bounded by 1 because that's a binary random variable. So we can write this way. Okay, so here what's left is how do you achieve equality? And what value of pi will achieve the equality? So in this particular case, so this we have it upper bounded by like this, and we want to now equality. How do we achieve equality? Right, that's what we need to know. And let me redraw that picture. So we can make use of selecting, we can select pi so that this data becomes half, okay? So, and we notice that there is a symmetry, then we can immediately say pi has to be half. But let's go slowly. And let's figure out what data looks like. Okay, data is defined to be y is equal to 0, right? So that is nothing but pi, pi times 1 minus p, 1 minus pi times p. That is data. And 1 minus data is pi times p plus 1 minus pi times 1 minus p. So that is the probability that y is equal to 1. Okay, so we have obtained the expression for data. Now let's go back to our question. When do we achieve equality? So here equality is achieved when pi is selected to be half. Let's try to take a look at it. What happens if pi is half? So this is half times 1 minus p. 1 minus pi is also half. These two are half. So this half times 1 minus p plus half times p. So half times 1. So this is half. So data becomes half. And then when you do the same here, the answer is exactly the same. So should be half. 1 minus data should be half as well. So we have proved that when pi is selected to be half, this is true. Okay, so select pi is equal to half, then equality is achieved. Since capacity is maximization of mutual information, by selecting the input distribution, we have found the input distribution, so the solution is complete. So capacity is equal to 1 minus h of p. Okay, and we can add the units. And we can also prove that if and only if. So this part as well. So when the equality is met, then pi has to be half. When the equality is met, these two should be half and half. And if we set this equal to half, pi has to be half. That can be done by solving this equation. For example, that is pi times p plus p minus p. That should be equal to half. And by collecting the terms with the pi and the term not related with p move to the right side, that is half minus p, and pi should be minus 2p at the denominator. 2. Half over 1 minus 2p. That's what is on the right hand side. So we can cancel these two. So pi has to be half. So we can finally say if and only if. So when you select input distribution to be uniform over the binary outputs of random variable x, you achieve the capacity. What is the capacity? 1 minus h of p. So summarizing the results, we have obtained upper bound 1 minus h of p by evaluating the mutual information. And we have shown that this upper bound can be met by selecting uniform input distribution. Since there exists optimal input distribution that achieve this upper bound, the capacity should be that upper bound. So C is equal to 1 minus H of P. Okay, so that is the derivation of the capacity for binary symmetric channel, right? We can do the same with a different approach. Let's say we can use this expression as well. This is expression. We have to evaluate what Px given y is. So in order to find these, what do you need to do? So you evaluate, you utilize the definition of conditional probability, and then you apply conditional probability numerator Py, right? But the Py can be written as Py given x, Px sum over x. So you can use Bayes' rule to find Px given y. Once you have this, then you can obtain the conditional entropy. So use this distribution right here to obtain this, and you summarize the relation between the first and you take the some difference of the two, and then you will come up with an expression, and then you can find the maximum mutual information by selecting uniform input distribution. That I think I should give as an exercise for you to do. So this is a tedious approach to get the same answer. Okay. So that's it. That's it for binary symmetric channel.